All right, let's get into it. For the longest time, a security standard called WEP was literally everywhere, protecting our Wi-Fi networks. It was supposed to be the digital equivalent of a locked door. But then this incredibly clever attack came along that could unravel the whole thing, using just a single piece of captured data. Today, we're going to break down exactly how this ingenious and kind of scary attack actually worked. So this is the big question, right? It just sounds impossible. How can one tiny packet, just a blip of data flying through the air, be the key to unlocking an entire encrypted network? It feels like something straight out of a Hollywood hacker movie. But as you're about to see, this was very, very real. And to really get why this was such a big deal, you have to see the before and after. Before this, cracking WEP was a game of pure patience. You had to sit there and slurp up millions of data packets, sometimes for hours or even days. But this new method, the fragmentation attack, it just completely rewrote the rules. We're talking about turning a multi-day project into a few minutes of work. It was an absolute game changer.
Okay, so to understand how they picked the lock, we first have to understand how the lock was built. Let's take a quick peek at the secret sauce at the very heart of WEP's encryption. So WEP used something called a stream cipher, and the basic idea is pretty simple. You mix your real data with a secret, constantly changing code to make it totally unreadable to anyone else. Think of it like a secret decoder ring that spits out a super long, random-looking string of characters. This secret stream was called the PRGA, and it was the key to everything, locking and unlocking the data. Let's just walk through it real quick. First, your Wi-Fi password, that's the secret key, gets combined with a little public value called an IV, and together they make a seed. Next, an algorithm called RC4 takes that seed and generates our special secret code, the PRGA. Then, in step 3, your actual data gets mixed with that code using this mathematical operation called XOR. And bam, the result is the encrypted data that gets sent over the air, safely, or so everyone thought. Now, pay attention here. Because this XR thing, it's the most important piece of the entire puzzle. It's a simple bit of logic, but it has this one magical property. It's perfectly reversible. What that means is if you have any two pieces of the equation, you can always figure out the third. This is the Achilles heel. This is the crack in the armor the entire attack is built on. And this is the relationship that matters. See, normally you mix the plain text with the secret PRGA to get the encrypted ciphertext. But because of that reversibility, if you could somehow get your hands on both the encrypted data and the original data, well, you could just mix them together and reveal the secret PRGA code. So that, of course, raises the million-dollar question. An attacker can easily snatch the encrypted ciphertext out of the air, right? But how in the world could they possibly know the original, unencrypted data that was sent? Let's see how they found that first crucial clue. This feels like the impossible step, doesn't it? The entire point of encryption is to hide the plain text. If an attacker already knew what it was, the security would be totally worthless from the start. So where could they possibly find it? Well, the answer was hiding in plain sight. It turns out, because of how networking standards work, almost every single Wi-Fi packet starts with the exact same predictable 8-byte header. It's like knowing that every secret message you intercept is going to start with the words, "Dear Agent." In the world of cryptography, this is the holy grail. It's called known plaintext. And that's the breakthrough. That is the aha moment. By grabbing just one packet, an attacker now has the two things they need, the ciphertext, which they just captured, and the first 8 bytes of the plaintext, which they already knew from the standard. They do that little XOR magic, and suddenly they can solve for the first 8 bytes of the secret PRGA code. It's just a tiny piece, but it's a start. Okay, so an attacker has 8 bytes of the secret code. That's not a lot, It's not enough to do much of anything. But this is where the pure genius of this attack really shines. Let's look at how they turn this tiny little crack into a massive, wide-open gateway. The attackers exploited a little-known and rarely used feature of the Wi-Fi standard itself, called fragmentation. Now, it was designed for a good reason, to break up big data packets into smaller chunks to make them easier to send, but the crucial part is that each tiny fragment gets encrypted all on its own. It was designed as a feature, not a bug, and they turned it into a devastating weapon. And this right here is the brilliant, vicious loop they created. First, the attacker uses their 8 bytes of known secret code. They craft a new message of their own choosing, encrypt it with that tiny piece of code, and send it to the network as a bunch of tiny fragments.
The access point, just doing its job, helpfully puts them all back together and sends out a brand new, full-sized packet. But here's the trick. The attacker is listening. They grab that new packet, and since they know the original message they just created, they can use the XOR trick again to recover a much, much larger piece of the secret PRGA code. They trick the network into giving them the keys. So, by running this loop over and over again, an attacker can generate as much of the secret PRGA code as they want, really, really fast. And once you can create that secret keystream on demand, you basically own the entire network.
This quote from Andrea Bidow, the author of the original research paper, it just says it all. The whole sense of safety people had was based on this idea that attacks were slow and difficult, but the fragmentation attack just completely shattered that assumption. Hours became minutes. The threat was now immediate.
And with this incredible new power, attackers had options. They could decrypt traffic byte by byte just by making clever guesses and watching how the network responded. Or they could create a massive flood of new data to feed into those old, slow statistical attacks, letting them crack the main WEP key with insane speed. They could even build a complete dictionary of keys, which would let them decrypt everything on the network without ever even needing the password. Game over. And when I say a flood, I mean a flood. The tool they built to automate this whole thing could forge and inject traffic at a rate of 950 packets per second. That is a tidal wave of data created out of thin air, all designed to just shatter the encryption. Just look at these numbers. This table shows the devastating result. A standard 40-bit WEP key, the kind that millions and millions of people relied on, could be cracked in about 2 minutes flat. Even the stronger 104-bit keys could fall in under half an hour. This wasn't some theoretical academic exercise anymore. It was a practical, repeatable, and shockingly fast way to break into pretty much any WEP network on the planet. Now, WEP is long gone. We've moved on to much stronger standards like WPA2 and WPA3. But the story of how it died, how it was so completely broken, offers a security lesson that is absolutely timeless. And this, right here, is the ultimate takeaway. The system wasn't broken by some brute force hammer. It was elegantly dismantled using its own rules against itself. The attackers didn't have to break the lock. They just exploited features, the predictable header, the fragmentation option, that were there in the open all along. It's the perfect proof that a complex system is only as secure as its most overlooked, seemingly harmless assumption. And that kind of leaves us with a final and, frankly, a pretty chilling thought. The engineers who built WEP were smart people. They thought it was secure. They followed the rules. But a tiny, overlooked interaction between two standard features brought the whole house of cards down. So it really makes you wonder, doesn't it? What feature of a system that we use every single day is just waiting for the right person to look at it in a completely new way?